So this is Unit 1, which comes from Chapter 2, the review, and this is video number 2. All right, so the table below shows the price X in thousands of dollars. So this is my X. So this is my independent. It's the X value of selected 2010 vehicles and their estimated city miles per gallon, Y. This is my Y value, which makes this is my dependent variable. Based on a linear model, we're not doing exponential or quadratic here, we're looking at linear. What is the expected price to the nearest 100, I'm rounding to the nearest 100, of a vehicle that gets 20 miles per gallon? Right, well, the first thing I have to do is I need a linear model, so I need to go to my calculator. Right, so I went to Stat and Edit, and I entered the data. Into list 1 are my X values, and into list 2 are my Y values. And then I'm going to go to Stat and Calculate, and I want a linear model, so I'm going to choice 4, Linear Regression. And I'm going to calculate. And just to make my estimate as accurate as possible, I'm going to round to 4 decimal places. So I'm going to say Y equals negative 0.2744X plus 29.4606. Now I do need to make sure I label my X and my Y. I've got to remember that X stands for price in thousands, and Y stands for miles per gallon. All right, and it says based on the linear model, what is the expected price? So I'm actually trying to find X for a vehicle that gets 20 miles per gallon. I'll tell you right now, this is one of the most missed problems every year on the test. Everyone just puts the 20 in for X. But 20 is not the price in thousands, it's the miles per gallon, which means this is going to be 20 equals negative 0.2744X plus 29.4606. So what I'm going to do now is I'm going to solve this equation. I might go into my part B space here a little bit. So the first thing I do to solve this equation is I'm going to subtract the 29.4606 from both sides. And I'll go to my calculator. So 20 minus the 29.4606. And that leaves me with negative 9.4606. Alright, so I was left with the negative 9.4606 equals the negative 0.2744x. I'm going to divide both sides by the negative 0.2744. And I'll see what I get for x. Right, so I'm going to use my calculator to do that. And I'm left with x equals 34.477. I have to remember that X is in thousands of dollars, so that's like saying $34,477. It says round to the nearest 100, which would give me 34,500 would be rounded to the nearest 100. All right. Part B, what is the correlation coefficient? To remember, correlation coefficient is R, that corresponds to the price and miles per gallon of the linear model above, which means I need to go back to my calculator, and I need to go back to my stat and calc, and I need to go to where I found my linear regression model and get the R value, which is negative 0.93. So R equals negative 0.93. Right, next problem. The table shows how many millions of miles motor vehicles drove in the United States in certain years. Determine a line of best fit. So once again, I'm going to do a linear model for the points in this data set. Let X represent the number of years after 1900. All right, so if I'm doing number of years after 1900, this column here would actually be 20. This would be 30, 40, 50, 60, and 70. So when I enter my data into the calculator, these are going to be my L1 values, and this column here would be my L2 values. All right, so notice I've entered the data into Stat and Edit, and I want you to notice the last entry in L2. I entered the actual value that's on the table, but the calculator in L2 shows it as 1.11 E6, meaning times 10 to the 6th. But notice how at the bottom of the calculator screen, it tells me the actual value that is an estimate of. So the actual value is still in the calculator, just in case you're wondering. So now I'm going to go to Stat and Calc, and I'll go down to Choice 4, because I'm doing a linear model. And there's my answer. I'm going to round. Let's just write down all the decimals since it's not a repeating decimal. So I get Y equals 20,011.44x minus 426,708.1333. Want to remember that X stands for years since 1900, and Y stands for millions of miles. So make sure you have labeled your equation. All right, so I've written down my equation and I've labeled it, and X is, again, years. Right. And the next question asks for the correlation coefficient, which means I need to look back at my calculator again. And the correlation coefficient is the R value, and I typically round to 2 decimal places, which says R equals 0.97. Right. And then it says determine a quadratic regression equation for all of the points of this data set. Quadratic regression. So now rather than linear, I want quadratic. So I'm going to go back to my calculator. Right, and I'm going to go to Stat. My data is already in the calculator. I'm going to go to Calculate, and this time I'm going to choose Choice 5, Quadratic Regression, as opposed to Linear. And I'm going to write down my Quadratic Regression model, which is Y equals, and let's see, let's go to 2 decimal places. 324.96x squared minus 9,235.38x plus 136,563.91. That's going to be my quadratic regression model. So here's my quadratic regression model. Still X is years since 1900, and Y is millions of miles. Okay. My next question says use your quadratic model. So I'm going to use my model from part C to find the residual. I remember right away that a residual is actual minus predicted. Well, the actual value in 1960 is 718,762. Now, I could find the predicted for just 1960 by putting a 60 into this equation, getting the value, and subtracting it. Or, if we want, we can use the calculator and use L3 and L4. It's really up to you. Since I only need one residual, I'm just going to put a 60 in here and figure out what this value is and subtract it. Right. So I typed everything in. Let's see, I put an extra 1 there. I'll delete that. Put everything in. I'll hit enter. And that is my predicted value. So my predicted value is 752,297.11. And since it's actual, I'm going to do my actual value, which was the 718,762. That was my actual value in 1960. And I'm going to subtract the 752,297.11. And that is going to be my residual. And I got negative 33,535.11. That is my residual for the year 1960. Then the question says, which model, linear or quadratic, better models the data? All right, so I'm going to need to go back to my calculator. And when I was at Stat and Calc for my quadratic regression, I remember that there is not an R, there's not a correlation coefficient, but there is an R squared, and it's 0.99 for the quadratic. So I'm going to check the linear model, and you have to compare it to the same thing. So let's see what the linear model's R squared value is. Since we can't compare R because quadratic doesn't have one. And the linear one is 0.94. So the quadratic's R squared was 0.99. The linear's was 0.94. So I'm going to go with quadratic because it has the higher R squared value. I'm going to say quadratic. The R squared is 0.99 for quadratic, which is closer to 1 than R squared equals 0.94 for linear. I could also compare some residuals if I wanted to, but I'm just going to compare R squared values for now. Right, given this equation, y equals 4.2 times 9/8 to the x, what is the initial value? This is always my initial value, so it's 4.2. What is the b value? That b value is the growth factor, that's 9/8. Is it growth or decay? It is growth because it is greater than 1. Let's go to my next question. Which correlation coefficient signifies the strongest relationship among a linear model? So positive and negative doesn't matter. That just tells me if it's an increasing or decreasing relationship. I want the one that's closest to either 1 or negative 1. And that would be A. It's very close to negative 1. And then looking down here at 15, we need to state the domain and range for each one. All right, I know that this is a line, and if I didn't know that, I could put that in my graphing calculator and see it's a line. And all lines have a domain that's all reals, as well as a range that is all reals.